Hi, my name's Andy Davis from NGS Secure. You may well have seen some of the other presentations earlier today from ISEC partners. ISEC partners are from the same group as NGS Secure. We're based in the UK, whereas they're based over in the US. And today I'm going to be talking about display hacking. So a quick agenda first. What am I going to be talking about? First of all, I'm sure you're all probably quite interested to know why on earth I'm talking about video interfaces and what that's going to do with security. We'll then go through a bit of history associated with the different interfaces I'm sure you're all well aware of. I'll apologize in advance that there's a huge number of acronyms associated with this world. And we'll be covering some of those. It gets a bit confusing when you've got acronyms of acronyms and that kind of stuff, you know, embedded acronyms within others. But, you know, bear with me on this. Hopefully I'll describe and explain what some of those acronyms actually mean. We'll then talk about how using KVM solutions affect some of the research that I've been doing. Talking about how you can fuzz EDID data, which is one of the protocols, kind of the primary protocol that I'll be discussing in the first half of the presentation, and then go on to some of the other protocols associated with HDMI that you may or may not have heard of, such as CEC, HEC, and HDCP. And then at the end, we'll bring it all together and hopefully make some sense from it. So why am I talking about video interfaces and how does it in any way relate to security? Well, it all started with some research that I was doing into the BlackBerry Playbook almost a year ago now. And at the time, I was looking at USB security. You might have seen some of the presentations that I've delivered on USB hacking at Black Hat and Infiltrate, conferences like that. So I was looking at the kind of hardware angle. There were various other people looking at the playbook in our company from different perspectives, but I was initially tasked with looking at the security of USB, which on this particular picture is the green interface in the middle. And RIM had done a pretty good job of securing the USB service or services that were listening over USB on QNX. So I started to think, well, yeah, what other interfaces have I got here? Well, a power connector with 3 pins, not necessarily interesting, potentially, but there's another one, a micro HDMI port. So I started thinking, well, you know, what can I do with this? I didn't really know much about HDMI. Obviously, I knew that it was a video interface standard, and I could plug it into my plasma TV and mirror the screen that was on the playbook. But I thought, well, let's investigate this and have a little bit of a more in-depth look at the protocol to see what could be done. So HDMI is an output, right? Well, yes and no. Obviously, it provides video out. That's its primary function, in conjunction with providing audio out. But then it has this ability to provide display information, this display identification and capability stuff. So allowing the display to tell the host what the capabilities of the monitor are. And that's sent via a protocol called EDID, which we'll talk about in a lot more depth in a minute. Now, I've got to apologize now because the original slides, it just said that the EDID data was an input. And that's primarily what I'm going to be talking about and the issues around this data that's provided into the host via this EDID capability. But there's also out as well, and I added out since I provided the slides to Black Hat, so you can manually add out to your slides when you get copies of them, because of a conversation I had with somebody recently, and I'll come back to that conversation a little bit later in the slides. But the primary thing to get across here is the first of the inputs to the host comes via this mechanism to have a look at the EDID information. You've also got a protocol called CEC, which is HDMI specific and allows data to come in and out. HEC, another protocol we'll be talking about, which allows data in and out. And an encryption and authentication protocol or group of protocols, depending on whether you're talking about HDMI or DisplayPort, which are HDCP and DPCP, which again are input and output. So it's not quite as straightforward as it first seems. It's not just providing information out to a display. So although I'm primarily talking about HDMI here, the EDID protocol that we're going to talk about relates to much older technologies, so the likes of VGA and DVI. And because it relates to all those different protocols, I'm going to go back and just kind of go over each one of those protocols and talk about the differences between them, the different interface standards, and how the things that I'm going to be talking about later on in the presentation relate to those. So looking at the display standards that have been around over the years, there's been lots and lots of different ones, going back to the 1970s and earlier. You've got the actual display standards, which talk about things like screen resolutions, color modes, refresh rates, that kind of stuff. But also the interface standards, and that's primarily what we're going to be talking about today, which cover things like the transmission protocols, what kind of compression's used or encryption schemes used, if they're digital rather than analog protocols. So let's go through each of the different video interface standards in turn. So first of all, VGA. Everyone is aware of VGA. It's been around for years. It's the standard 15-pin D connectors on the back of everyone's laptop. And the name's kind of synonymous with the video protocol and that particular interface. It's an analog video standard, bearing in mind it goes back to the 80s. So you've got separate red, green, and blue analog video signals and horizontal and vertical sync. Pretty standard, straightforward video provider. However, there are 4 pins that were originally classed as reserved, and the intention was, right from day one, that there was some kind of capability for the monitor to provide information to the host about what kind of monitor it was. And the original kind of very, very basic way that worked was bits were allocated to those pins, and you could have basically up to 15 different monitor types, but only 3 were ever defined, and it wasn't really used very much. And then the VESA, Video Electronic Standards Association, created a protocol called DDC. Now, it's DDC that's common across all these different interfaces and is still being used in a later iteration on HDMI. So that's why we're talking about these different interface standards. So DDC, Display Data Channel, used some of those pins to provide information about the monitor capabilities and characteristics back to the host in a much more kind of creative and useful way than the original. DVI, so this is a more recent interface standard developed by DDWG, and it's obviously a digital standard as opposed to the VGA analog standard. And VGA is now viewed as outdated and legacy, and it's still around on the majority of PCs, although now it's starting to get phased out on PCs in the last year or so that are coming out with DisplayPort and HDMI only. So DVI sends uncompressed video signals using a protocol called TMDS, but we're not going to go into that because it doesn't in any way relate to this talk. It's got backward compatibility with the analog capabilities of VGA. In some iterations, there's various different types of connector you can get with DVI, some of which support the backward compatibility and others don't, but that's, again, not really relevant. The thing to bear in mind just from a security perspective is that DVI also supports this DDC protocol. HDMI, I'm sure everyone's also aware of HDMI, probably more so with consumer electronics goods than necessarily IT equipment. If you've got a Blu-ray player or a plasma TV, it's going to have an HDMI port on the back. The digital video signal is the same as with DVI. It uses TDMS, but again, it supports this DDC protocol for display information data, and also supports a whole load of new technologies which haven't been implemented on video technology before. So you've got things like CEC, the Consumer Electronics Control Protocol, HDCP, high bandwidth digital content protection, the encryption side of things, and HEC, HDMI Ethernet channel. Again, we'll be talking about each of those in turn later on. And finally, DisplayPort. So I mentioned that more modern laptops are likely to have DisplayPort or HDMI ports on them. More likely than not, it's going to be DisplayPort these days. And the reason for that is because of the royalties that are associated with HDMI. So DisplayPort is a free, from the perspective of the equipment vendor, a free solution rather than having to pay for every implementation of an HDMI port. The image that you can see there, that little logo, the DisplayPort ++ logo, means that it also supports HDMI. So if you've got an HDMI to DisplayPort lead, you can plug it into your HDMI capable plasma TV. It's packet-based, so it doesn't use the DVI transmission standard that's used in HDMI. It does support DDC again, also HDCP and DPCP, which is the DisplayPort equivalent of HDCP on the encryption side of things. It doesn't natively support CEC, but you're probably all getting fed up with me talking about all these acronyms, and please tell me how this fits into security. Well, there's a little bit more that we need to go through before we get to that. DDC that I've been talking about, this display data channel that allows the connected to this display to talk about its capabilities to the host. So I'm sure you've all seen, when you plug your laptop into an external display or a projector like this, there's a short delay while the host kind of works out what's going on, and kind of the screen might go blue, and then eventually it displays the image on the external display, or comes up with some kind of menu asking you, how you'd like to display the data. Or what's going on in that delay period is a plug-and-play process whereby the EDID data from the display that you've just plugged in is sending the data to the host, and the host's thinking, what can I do with this data? What's the best resolution I can use based on the monitor that's just been plugged in? All that kind of stuff. So at the point that you connect the monitor, you get, as an absolute minimum, a 128-byte block called an EDID visa block, which is sent from an EEPROM, or an E2 PROM, more likely, which is inside the monitor electronics. So at the point you plug in, the power from the video port is sent up the cable. That powers up the E2 PROM and says, give me this data about the capabilities of the monitor. So there's a few different versions of DDC that allow this to happen. Version 1, which continuously sent this EDID block rather than just at the time when it was plugged in, and hardly anyone actually adopted DDC 1, so we'll move on to DDC 2. various different subversions of this. The one that you're most likely to encounter as a result of plugging in a monitor is going to be DDC2B. And this uses the I2C bus, which is the integrated circuit bus, a very simple communication mechanism for allowing ICs to talk to each other on a motherboard normally. It's two-wire. You've got a data line and a clock line. And as I said, at the point when you plug in the monitor, the plus 5 volt line on that monitor cable powers up the monitor, or powers up the chip within the monitor so that it can provide this data back to the host. And the whole reason behind that is even if the mains power to the monitor is removed, the EDID data and the capabilities of the monitor can still be identified by the host, because it's purely just that single circuit with the E2 prom on that's powered up by connecting in the monitor cable. And those SDA and SCL pins for DDC are present on all the different interface standards that we've talked about. But of course, the vendors said, we need to send more data. 128 bytes isn't enough. There's a capability, and the vendors say, yeah, okay, let's see how much we can leverage out of this. So eDDC was born, Enhanced Display Data Channel. So this allows you to use a segment pointer to address up to 32K of data rather than just 128 bytes. And therefore, they extended the EDID protocol, which is the protocol that determines the structure of the data within the block. So you can have multiple blocks, that kind of stuff. So a standard EDID block is 128 bytes, as I said. And EEDID introduced this concept of extension blocks, which are also 128 bytes in length. So DDC2 allowed a single EDID block, the Visa block that I've talked about, followed by one extension block. But EEDID, as that should be, not EDID, now allows you to supply 256 128 byte blocks, so significantly more data. And as we all know, the more data that you provide to a host, the more parsing is involved to understand that data, and parsers equals potential vulnerabilities. So what does an EDID Visa block actually look like? Well, first of all, you've got a header, which is just fixed 6 bytes of data. You've got vendor and product information, the version and revision number. So the latest version of EDID is 1.4. Video input definition, transfer characteristics, color characteristics, all this different information. You get a concept of descriptor blocks, which are optional, and you can have up to 4 of those, and they can contain different variable bits of information. There's an extension flag which says, are there any more blocks after this block? And a checksum. So a whole load of data that can potentially, or data that needs to be parsed and understood and manipulated by the host. There are a bunch of standard extension blocks, and it's just worth pointing out that all the standards associated with these are provided by Visa. Some of these can be downloaded from their site, some of which you've got to pay for, but it's all kind of set out in black and white how these different blocks are supposed to be formatted and how they should be used in conjunction with each other. But one particular extension block stood out as being quite interesting, the localized string extension block, because there's the potential for putting lots of string information in there, and certainly the potential for buffer overflows. And I'll show you an example of what a localized string extension block looks like in a second. However, when you're using these blocks, there are a number of different rules that must be followed. So the visa block, that first one that I talked about, is always required, and that always has to be the first block that's sent. You always need to have at least one CEA extension block. That first one up there, which is kind of provides more information of what's in the visa block. If you've got more than one extension block used, they have to be the same version of EDID. And if you start using lots of extension blocks, you need to use a special extension block called a block map, which describes the structure of all these blocks and how they fit together and what order they're in. So again, you're seeing more and more kind of complication here of information provided. So this is an example of a localized string extension block. And as you can see in there, not only have you got strings, but you've got lengths associated with the corresponding strings. And I'm sure you can all see the potential for buffer overflows there if that data isn't correctly parsed. KVM solutions, what effect do they have? Well, so KVM, keyboard video monitor, video mouse, sorry, extenders. What happens to the EDID data when you've got one of these involved, when it's sat between your PC and a display? There's three different scenarios. The first one, and there's no support at all. If the KVM solution isn't looking at the SCL and SDA lines, those the DDC lines, and not interpreting any of that data, then it's not going to be able to cope with it at all, and it's not going to be able to provide the information through from the monitor to the connected host. Some of them use a concept of fake EDID. So the KVM switch decides what an ideal world EDID block will look like, but it might not necessarily be appropriate for what you want. And then finally, you've got a scenario of pass-through where the KVM switch understands and interprets the EDID and then attempts to send that through unmodified to the host. But this can cause all kinds of problems as well, because you can confuse the host when it kind of tries to redetect the display, and sometimes you can confuse the display and it goes into a power save mode. So basically the moral of the story is if you're doing any of this kind of research, just don't use KVM solutions. They can cause chaos. I was going to that little conversation that I had recently, I'll come back to after I've talked about the fuzzing stuff, I think. So what we need to do to be able to fuzz EDID and provide this data in a valid sense, albeit malformed, to a video interface, we need some kind of capability to emulate a monitor and emulate DDC. So the solution that I came up with was using a microcontroller, the Arduino Duomilanove, and this was purely down to the fact that some of the USB research that I'd been doing, I'd used one of these and I had one lying around handy. And also, quite usefully, the I2C bus is supported by default in a library called Wire. So there are a number of other challenges that I needed to sort out before I could fuzz EDID successfully. First of all, I needed to replicate this eDDC protocol. Yes, I can talk I2C, but DDC communicates over I2C, so I need to make sure that the Arduino is talking it correctly. I need to emulate the attachment and detachment of the display, because the data that I want to send for each fuzz test case is going to be sent at the point of insertion. So I need to emulate insertion and removal so that so I can iterate through the different fuzz test cases. And obviously I need to go through the different elements within the different EDID blocks and manipulate that data to create my different fuzz test cases. So replicating the EDDC protocol, there were some changes that I needed to make to the wire library in order to get it to talk DDC. There are only relatively minor changes, changing buffer sizes, that kind of thing, but I managed to get that working relatively quickly. Another thing that I needed to do was on the Arduino, there's some internal pull-up resistors that are used by default when talking to the I2C bus. They were the wrong value for what I needed to, so I just disabled those and used my own external pull-up resistors instead. And then I need to configure some interrupt handlers to process the incoming messages and for when the data is required on the I2C bus. So when it came to emulating the attachment and detachment of the display, this was very easy on DVI, HDMI, and DisplayPort because there's a hot plug pin. So essentially, when plus 5 volts is attached to the hot plug pin, i.e., when it's connected in, the device knows that it's connected. And so you can virtually unplug and plug in the device by toggling that hot plug pin high and low. That's not the case on VGA, but what I found was the devices that I was fuzzing that had VGA also had DisplayPort, so I was fuzzing using DisplayPort, and then if I find an interesting test case, I'd then go back and do like a one-shot attempt with VGA. But it's something that I haven't successfully automated with VGA yet. And then, of course, iterating through the different elements of the EDID block, that's straightforward. Within the firmware that I wrote on the Arduino, you can just loop through and manipulate the data and create the different fuzz test cases as you like, and then use the built-in serial interface to provide feedback to you as to kind of what the current fuzz test case is, that kind of thing. So very straightforward circuit. Basically, all I needed to do was provide those external pull-up resistors and then connect to the appropriate SCL and SDA pins on each of the interfaces, and then back to the Arduino. That's a photo of my actual device. I didn't bring it with me because I don't like taking random black boxes through airports. They tend to get a bit twitchy. The firmware for the fuzzer can be downloaded from our website, from the research section. And yeah, feel free to have a play with that and see what you can do with it. Within the firmware, it contains all the details of the different extension blocks to play around with. And so yeah, feel free to see what you can do. So what I've actually found with it? Well, as I said, it all started off with BlackBerry Playbook. And unfortunately, there weren't any standard buffer overflows associated with the localized string extension block. That would have been fantastic and probably been exploitable as a result, but that wasn't to be the case. So as I was fuzzing through the Visa block, I was taking a pure kind of brute force bit flipping approach and monitoring the state of the host. And it stopped responding as a result of one particular EDID block that I sent. And I've got to point out here that this particular bit of code that I'm showing you isn't the exact bit of code within the playbook that caused the bug. It's the same class of issue as this. So it looks a bit like this. And the reason that I can show you the source code at all is because the bug is in an open source library. It wasn't written by RIM. So they implemented it, and it's been implemented in various other things as well, because it's open source code. But as you can see, it's a Friday afternoon bit of code, and the Y++ should have been X++, and it resulted in an infinite loop. And now you're all probably sitting there thinking, well, congratulations, you've managed to do a local DOS on the HDMI port on your playbook. Well done. However, as a result of that bug, it triggered a secondary bug which killed the system logger daemon. A thing called slogger on Qnix, which is essentially the same as syslog D. The initial bug has been fixed by RIM, but this secondary bug that killed the logger daemon hasn't been resolved yet. It does seem to be HDMI, in some way HDMI specific, in that they haven't managed to kill the logger daemon by any other means, trying to replicate what happens as a result of this infinite loop. But as I'm sure you can all appreciate, the ability to knock out all logging on a playbook just by plugging in a rogue monitor is quite an interesting capability. NVIDIA Windows driver, I've managed to gain a whole load of different crashes associated with the Windows 7 kernel mode driver. But it's very difficult to pin down exactly what's going on and what's causing these crashes. I haven't seen any one case so far where you can directly map a specific entry within an EDID block to the crash occurring. So this is kind of like work in progress, and none of that information has been provided to NVIDIA so far, so I'm not going to go into technical details of exactly where the area that we're investigating that's causing these issues. But needless to say, based on what I've talked about with the other interface standards, you can trigger this over the VGA port, and we've demonstrated kind of multiple examples of test cases over the VGA port which have caused some of these crashes. So potentially quite interesting if we can get to the bottom of them. Yeah, just one mention before I get onto the CEC protocol about this conversation that I had about the DDC protocol, and I was chatting to someone about EDID and the fact that you've got all this EDID data coming in that's being processed by the host, and the guy I was chatting to said, "Oh, have you looked at the MCCS protocol?" I was like, "No." So I had a look at that. MCCS is the monitor control command set, and this is a capability that allows your host to configure your monitor or capabilities of your monitor via DDC. So some monitors have got write protect capability enabled, a lot of them haven't. Now, if you haven't got this write protect enabled, then an attacker that has compromised your machine or has some capability to send data from your machine to your monitor can essentially nuke your monitor. If you wipe out the EDID data, your monitor just won't work. You plug it in and you'll just get a black screen. So taking the kind of denial of service attack scenario of you want to stop somebody from using their PC, rather than trying to stop them using the operating system, you could always stop them from using their PC because they can't see anything on the monitor because the monitor doesn't work, purely by sending random data to their EDID blocks on their monitor. So consumer electronics control. This is one of the HDMI specific protocols, allowing you to control multiple HDMI devices with a single infrared remote control. Devices can also communicate with each other via the protocol without the user getting involved. It's set up as this kind of inverted tree structure. The root node's always the display. You then have branches, which are things like video switches. So for example, if you've got an AV amp that's switching audio and video, that would be a branch. And then leaf nodes are things like your Blu-ray players, DVD players, that kind of thing. So the whole concept of this is the user only needs to perform minimal number of actions. So if you want to turn the volume up and you're watching a movie on your Blu-ray player that's going via an AV amp to your plasma TV, there's multiple devices for which the volume control on the remote will modify the end result. But you want to just be able to hit volume up and let the system decide which is the best thing to turn the volume up. And that's the way that it works. So the user hits volume up, and then via CEC, the devices communicate with each other and work out the best way to make it louder. It runs over a one-wire bidirectional serial bus using the AV Link protocol. And you can have up to 10 physical devices connected. And just a little bit about the actual protocol itself. There's a concept of physical addressing and logical addressing. You've got essentially 4 bits which represent the source address of a device when you're going to send some CEC command. So the first byte that you'll see on the wire, you have the first 4 bits of that byte, which is the source. The second 4 bits is the destination. You've got a concept of broadcast addresses, just like you do with Ethernet, so you can send to many. And then you've got an opcode, which is a command, and then a variable amount of data. But what's very interesting looking at the standard is that even within the initial standard, you've got an opcode which represents user-defined, so kind of vendor-defined functionality. And although a lot of devices implement CEC, and probably many of the devices that you've got connected in your AV setups at home support CEC, you'll never see CEC mentioned on any of the products. They'll all have their own names like Sony, Bravia Link, and all this kind of thing. And they're all slightly different because they've used their own kind of proprietary extensions to the protocol, which makes it potentially interesting from a security perspective. So what sort of things can it do? There's a whole load of standard things that it's designed to do, all the kind of things that you'd expect from a protocol that's allowing you to do kind of minimal things. So yeah, I won't go through and talk through them all, but the main thing is that it's quite a full-featured protocol, feature-rich protocol. And potentially could yield some interesting security vulnerabilities based on the fact that it doesn't seem to have been designed specifically with security in mind. It's designed with usability in mind. So can we fuzz it? Well, there's an Arduino library that somebody has kindly put together that talks CEC. There's plenty of people out there that want to be able to get their PC to talk to all their AV kit via this protocol. And there's even a nice circuit that somebody's developed to use with the CEC Arduino library. However, there's also commercial solutions which are very inexpensive. There's a product from a company called Range Shadow in the US, which is, I think it's about $60, something like that. And it's literally just a USB to CEC bridge. And there's also one from a company called Pulse8, and they've developed their own library called libcec that communicates with that. So I'm in the process at the moment of developing a CEC protocol fuzzer using libcec. Unfortunately, it's not in a state in which I can release it, but once it is, I will be publicly talking about it and releasing it so that you can all play with it. A couple of other protocols that are associated with HDMI that I'm going to talk about. First of all, HDMI Ethernet channel. Introduced HDMI version 1.4, so relatively recently. It's something that's quite new in the standard. So the whole concept is it allows you to include the data stream associated with Ethernet within an HDMI cable. So if you've got two devices that are connected together, let's say you've got an internet-enabled TV, and that's connected to your home broadband via wireless, and then that's in turn connected to a Blu-ray player, and the Blu-ray player has the ability to do updates over the internet. It can connect to the internet via the HDMI cable using the HEC protocol because it's connected to the TV, which has got internet access. So it's all about reducing cables, essentially. But the way I look at this is quite interesting. If you've got like these kind of home mini AV networks that are all connected to your home broadband, maybe in the future this, rather than just your home PC become part of a botnet on the internet, you may well have kind of AV botnets as well, all these extra devices getting connected. And finally, for completeness, HDCP. So this is a copy protection that was developed by Intel Corporation to stop copyright theft associated with digital content. So the design is to stop digital equipment being developed that could receive digital content and then therefore copy that off to a form in which it didn't have any kind of encrypted protection. It uses three different cryptographic mechanisms. Firstly, authentication. So this is this concept that I've just mentioned, preventing non-licensed devices from receiving the content that they could then do something nefarious with. Encryption, so it prevents any kind of eavesdropping on the wire, man-in-the-middle attacks. And then key revocation. So if you have a device that has been compromised, you can then prevent that device from no longer receiving any encrypted content. So back in September 2010, an HDCP master key was disclosed on the internet. And that key revocation mechanism that I talked about has therefore been rendered useless. Theoretically, if somebody produces a device using the information that was leaked. What was very interesting, though, was that the anecdotal evidence, initially people thought that that key had been leaked, it had been stolen from somewhere and then put on the internet, but it appears that it was most likely reverse engineered as a result of a vendor producing these devices, having a certain number of device keys, and using the information in those device keys, you could work out what the original master key was, which is quite interesting. So to wrap it all up, in conclusion, the vast majority of people are totally unaware that video displays that they're plugging into their laptops actually send data. They just expect everything to go out to their monitor. They're not expecting their monitor to be sending them stuff that's then getting processed on their laptop. We can see that in this kind of plug-and-play world, users are expecting more and more seamless functionality between these devices, and there's going to be a much greater need for communication using these protocols. There are vulnerabilities in EDID parsers and potentially these CEC parsers, and hopefully I'm going to find some with my CEC fuzzer once I've got it going. So a few areas of future research for us. We've only really kind of looked at basic sets of EDID blocks and data within them. There's a hell of a lot of different information that can be provided in EDID blocks, and lots of potential creative combinations of blocks that you could set up using that block map block that you need if you've got multiple blocks. So I'm sure there's potential scenarios whereby You've got memory being dynamically allocated based on the blocks, on the number of blocks, and all that kind of stuff. So that's something that we need to look at. Certainly adding a bit more intelligence to the fuzzer at the moment. It's a pretty basic fuzzer at the moment that allows you to do pretty simple kind of brute force bit flipping based on different areas within EDID blocks. Yeah, it'd be quite useful to identify a technique to emulate the insertion and removal of a VGA cable, just for a kind of legacy capability of demonstrating this kind of stuff via VGA rather than via HDMI. And of course, yeah, complete the CEC fuzzing project and test it against a whole load of different devices that understand CEC. So, yeah, I've really only scratched the surface of these technologies and what you can do with them. And hopefully by providing the details of the fuzzers that I've produced and you can download and make them yourselves and get going, hopefully it's going to encourage more research in this area, because it's something that doesn't really seem to have been touched on much before. There's an accompanying white paper which you can download from that URL there or from Black Hat. It's the same one that's going to be provided by Black Hat, so it'll be on the CDs and available on the internet. Has anyone got any questions? Yep.
So, HEC, did you get the opportunity to investigate any consumer AV devices that have it? I'm thinking of what ports they might be listening on for what.
Yeah, it's something that I probably should have included within that bit at the end of stuff that we need to continue looking at, because I haven't looked at HEC in any detail. It's still very new. I'm not really sure how well it's been adopted so far, and indeed, how well it integrates with things like Windows 7. If you just plug a laptop into, let's say you've got an internet-enabled TV that's connected to your broadband via wireless, and then you plug your laptop into the TV via an HEC-enabled HDMI cable, does it pop up with a new interface on Windows 7? That's something I need to find out, because, yeah, there's certainly a lot of things that you can look at there. Any other questions? Yep.
With the HDCP devices,
yeah.
have you seen any physical segregation from other components of HDMI sort of devices, insofar as if you were to compromise something and make an SS12 memory reads or writes, would you be able to recover cryptographic activity?
That's an interesting one. So if you compromise the device in some way, maybe via a CEC bug or something, and you had control of the device, could you then access the cryptographic data within HDCP? Potentially. I haven't looked into the architecture of specific devices to see if they've gone that extra mile to make sure that that's segregated off. But it would be interesting to know whether they have catered for the scenarios whereby people are trying to attack the machine via these different protocols. Because, as I said, it's not something that I've seen presented anywhere else. So I'm not sure of the mindset, the kind of the level of security awareness of the people who've designed these kind of products. But yeah, certainly something interesting to look at. Okay, thanks very much. Oh, sorry, another question. Yeah, go for it.
So you said that once upon a time the EDID block was hardwired into an EEPROM or something, but presumably nowadays it's actually supplied by a microcontroller and will be processing behind what decides to send.
I think, as far as EDID goes, it is still in an E-squared PROM. It's still pretty basic in as much, it's a dumb thing that gets provided with data, provided with plus 5 volts, it fires up the chip and squirts back the data. So
what I was wondering was, so by your mechanism for wiping the EEPROM or replacing it with invalid data or breaking the monitor,
yep.
whether you could instead cause the controller, the time was
Yep. If they continue to extend this protocol, I mean, it's been extended a couple of times. You know, if they want more and more data, then theoretically that scenario might present itself in the future, rather than just the kind of dumb memory providing data out scenario. You have a microcontroller on the end instead. And in that case, then, yeah, that certainly would be an interesting scenario, trying to compromise the microcontroller embedded within a TV. Great. Thanks very much.